Okay, so for this example, we want to go and model an LR circuit and then use it to answer a question. And the first thing you'll notice in all these examples here is that although we have 3 components in our circuits, all these problems will have just 2 components because we're looking at first order equations. So you'll notice that we have an inductor and a resistor, so that makes this an LR circuit. So using our equation, our R is going to be equal to our resistance, which is 6 ohms. So we've got 6 times I plus our inductor, which is 2 henries, times our I prime, which is di dt, and that is equal to our electromagnetic force, which is 20 times e to the negative 0.25 t. And you'll notice that all these equations are going to be linear. So the first thing we want to do is put it in our standard form. So we'll just switch the 2 first terms around. So we've got 2 I prime plus 6 times I is equal to 20 e to the negative 0.25 t. Then we'll divide the entire equation through by a 2 to get the I prime leading the way. So we've got I prime plus 3 times I is equal to now 10 e to the negative 0.25 t. Our integrating factor is really simple. It's just going to be mu of t is equal to e to the integral of 3 dt, which is just e to the 3t. So we multiply that through our entire equation, and e to the 3t times I prime plus 3 e to the 3t times I is equal to 10 e to the 3t times e to the negative 0.25 t. Like always, we rewrite this as a derivative of a product. So that's e to the 3t times I. That's been differentiated. And over here, we can combine our 2 exponentials together by just using addition. So that's going to be 3 minus our 0.25. So that's 2.75, of course. So that's e to the 2.75 t. We now integrate with respect to the independent variable. So that is going to be with respect to t. And in doing so, we end up with e to the 3t times I is equal to 10. Now divided by 2.75, which comes out to be a nasty decimal, so I'll convert it to a fraction, and that is 40 elevenths. So that's 40 elevenths e to 2.75 t plus a constant c. And then last step, of course, dividing through by the exponential. And we end up with I of t, our current, is equal to 40 elevenths e to the negative 0.25 t plus a c e to the negative 3t. And they tell us in the problem that we have no initial current, so I of 0 is equal to 0. So 0 is equal to 40 elevenths plus c. C is negative 40 over 11. So our current is going to be I of t is equal to 40 elevenths times the quantity e to the negative 0.25 t minus e to the negative 3t. And that is the current on our circuit at any given time. Now, in the interest of time, we won't go through and find the charge, but if you wanted to find the charge, all you'd have to do is go in and integrate this. So the charge would be Q of t is equal to the integral of the current I of t with respect to t. And then, of course, we would use another constant and solve another initial value problem. All right, so that's our LR circuit.